minutes of their life they've spent in the moon shadow, or how many totalities they've seen. And there are some people that are really bad at that, like Jay Pastikov. I mean, he'll drop that every time you talk to him. He'll tell you that he's seen more totalities than anyone on Earth, which isn't even true, because Fred Espenak has, and he's a really nice guy, and he won't even say that unless you kind of force it out of him. So I don't want to be in that category of telling you, well, I've been to blah, blah, blah eclipses. I'm going to avoid that and just say, because it's germane to this, is that the number of people that have taken along to eclipses since 1970, the first one, is so many that I've come to see what people are into, what people need to know and don't know, what are the odd things about totalities that I didn't learn until my 5th or 8th or 11th total eclipse. And I know some of you have never been to one, and some of you have been to several. So there's a range of experience in this room, and I honor that. But whichever of those categories you're in, there's stuff that I think you might find useful. So I'm going to just use these 15 minutes to share that with you. For example, I'm just doing this in a desultory, free associative way. The diamond ring. Everybody wants to see the diamond ring effect. But some textbooks say, don't look at the diamond ring. You'll hurt your eyes, because that's direct sunlight. It's only a spot of direct sunlight, but it's direct sunlight. So it's dangerous, it's perilous, and we all value our eyesight. And one of my readers of my son book some years ago contacted me to say that one of his eyes was actually ruined by injudicious use of, till he was sweeping near the sun looking for Mercury. And the telescope went across the sun just for less than a second. And it was enough to ruin the eyesight in one eye permanently. So we have to be careful, but does that mean forget the diamond ring? No way. We're going to see the diamond ring. I know you're going to. And the reason it's important to see it, see, I don't want to be sued either, so I shouldn't say it's important to see it. I'm going to say if you decide to take the risk to see it, okay, is because photos don't show it. There are some things in life that photographs capture. The Taj Mahal, for example. If you go to the Taj Mahal or to Machu Picchu, the one amazing thing you'll say to yourself is, this looks just like the pictures. It's almost like, okay, why am I here? It's exactly like the pictures. But the diamond ring is not. Photographs show a different thing than what you'll see. Now, there's two reasons for that. One, there is and this sounds hippie-ish, but we live in Woodstock. So one of them is the vibe of it. There's a feeling that comes in total eclipses. Totality is a sacred event. So beyond the science, beyond the logic, beyond the things to look for scientifically, there's also a feeling that knocks you backward. About half of the people in our totality tour groups over the years, half of them I've noticed weep during totality. You know who weeps during a partial total eclipse? Nobody, unless their shoes aren't fitting right or something like that. There's something about it. I mean, if you love nature anyway, and you can be swept away by the Grand Canyon or something, or a rainbow or something like that, and you've never seen totality before, it's something different from anything else in nature. It will touch your spirit. One of the people in our 1980 total eclipse tour to India afterward said she thought of it as being the home of her soul. That's how she felt it. And I have every confidence you'll feel the same thing in your own way, in your own language for this. It's a wondrous experience. And it's one of the reasons you don't want to cut it down. I mean, you guys have about a 3-minute totality here. Now, you wouldn't deliberately cut that down to 1 minute, would you? I mean, you wouldn't deliberately say, all right, let's go to the edge of the path of totality and make it only a 1 minute eclipse. Yeah, want to come with me and come down? I wish I had to Geneseo. I thought of a place that's probably closer to the edge. Let's go to Geneseo and see it from the private airport down there. Then we'll only have 1 minute. But some of you will do that. You know why? Because some of you are going to take pictures. And the experienced eclipse people and the professional eclipse watchers, the advice that we always give is don't take pictures. Unless photography is your thing and you're like, it's important to you. Then I'm not going to say don't take pictures. But if you're taking them because of either pride, oh yeah, I want my own pictures, because you should know there will be people taking pictures that will do a better job than you will. There will be photos of the same eclipse you're going to see, but better ones that you're going to come up with. So if you want a record of it, that's going to be available afterward. Here's what will happen if you take pictures. To do it decently, you have to bracket the exposures because the corona is of one brightness, the diamond ring and the prominences are another. You have to do a different series of f-stops. And that means, and you may even want to change the size of the solar image. You're going to be changing lenses. You're going to be looking down and twiddling f-stops. You're going to mess up and you're going to readjust things. And you're going to end up looking down and looking away for at least half the time. You're going to change that 3-minute eclipse into a 1-minute eclipse. So my first advice is don't do it unless you have to. Unless photography is really important to you, then of course, go ahead. But otherwise, don't. In fact, some professional astronomers like Bart Bach, who went to many, spent his last eclipse realizing how often he'd been fiddling with equipment and spectrographs and things like that, and deliberately spent his final eclipse just sitting and leaning back and just looking up at that sacred site. Sacred site. It'll just knock you backwards. Back to the diamond ring. So here's the thing. You can't really well expose the diamond ring because it is so much brighter. We're talking about 100,000 times brighter than the corona. So to capture both is impossible. You're going to underexpose one or overexpose the other. So if you get the right exposure to also have the corona in the picture, which you want, otherwise it's not going to look like an eclipse picture. You want the black moon, you want the corona, and you want that spot of brilliant sun. That means to capture the corona, you're going to overexpose the diamond ring. Now, how does an overexposed spot of sunlight look on a picture? Does it look brighter on the picture? It can't look brighter because the paper or the screen that you're looking at is only so white. It's not going to get brighter. So what it does is it flares the image. And so every photograph of the diamond ring effect shows a big blob of sun. That's not the way it looks. One of the reasons it's so wondrous is that you see that black disk of the sun, you see the corona, and you see a star-like point of light. That's the most brilliant thing you've ever seen juxtaposed against all that delicateness. And it's that tiny size of the diamond ring that's a good part of its charm, of its magic. You don't get that on photos. You get a big blob instead on photos. So if you want to see the diamond ring, see the diamond ring. Don't try to photograph it. Plus, to photograph it, all right, enough about how the photos don't match it. I mean, photos are often like that. You know, they can capture some things, as I said, like the Taj Mahal or the Machu Picchu. But there are many things in life that can't be. It just isn't the same. You got to be there, as they say. And eclipse is one of them. And while we're talking about the diamond ring, let's talk about the safety of it, because as I said, some books say it's not safe. Is that true? Well, we did a bunch of research in Astronomy magazine. We had some experts on eye safety. And before that, about 15 years earlier, for an article in Discover magazine, I was the monthly columnist in Discover for 17 years before Astronomy magazine. And what it turns out is that, first of all, the safest filter, if you want to use welding goggles, is 12, 13, and 14. Ignore all the wrong internet info that says only a 14 is safe. In fact, when we've offered guests on eclipses a choice and given them a few the day before the eclipse to look at the sun and see which they like best, nobody prefers a 14 because the sun's image is too dark. It looks too dark. It's much sharper in a 12, and it's safe in a 12. All the experts and all the testing show that you can use a 12 for 26 straight hours of looking at the sun. and meet the international standards for eye safety. So your choice is 12 or 13. But here's a secret. There's also a 13. That's a rare welding goggle because they usually sell even numbers. But if you go ahead of time and don't wait till the week before the eclipse and go to your local welding supply store, which is usually in the most rundown part of town, usually with barbed wire fence and snarling dogs and stuff like that. And you go there and you want to order a bunch of them. They're only a few dollars each of 13s. You can get them. They'll get them for you a week later. And I sent a bunch of 12, no, wrong. I sent 12, 13, and 14 to Astronomy Magazine about half a year ago. And I wanted the entire staff to look at the sun and see which image they preferred, to see if they felt the same way that I do and other members of our last few eclipse tours have. And they felt the same way. The 13s give the best image, according to me and most people. Try it yourself. Now, why would you want a welding filter instead of a floppy plastic lined with cardboard, the most common filters that you get these days? Well, first of all, those can scratch easily, and you don't want to get any part of the sun's image on you. They do have the advantage of usually having a nice yellow or orange image, whereas welding goggles have a greenish image. So there is that one advantage to those floppy cardboard ones. But I always like the image quality of the glass, that's shatterproof glass, welding goggles. And unless you get the whole helmet, which you don't need unless you're going to be repairing your car at the same time or something, just get the filter for like $2 each. So 12, 13, or 14, get them ahead of time. Okay, now to the diamond ring. You can't use those to see the diamond ring because the diamond ring will just be a spot and you won't see anything else. I mean, there's no aesthetic pleasantry in that. So, of course, there's usually 2 diamond rings unless it's a very short eclipse. If it's a short totality, that means the moon and the sun are almost the same size. The moon happens to be farther away than its average distance, and or the sun is larger than its average distance. In other words, let's say you're doing it in January, there's an eclipse in January, the sun is going to be at its largest. A large sun, a large moon, smaller sun makes for a longer eclipse, but the opposite can make for a very short eclipse. Now, short totality usually gives you Bailey's beads. A longer eclipse will almost always give you a nice diamond ring. One at the beginning, one at the end of totality. Now, it's the one, let's talk about the one in the beginning. So here's the thing to look for. During that hour-long partial but growing eclipse of the sun, you'll of course be using your eye protection the whole time. You don't want to look at the sun at all. And things get interesting for the final 10 minutes before totality, especially the 5 minutes before totality. I'm directing this primarily people who have never been to a total eclipse. Those of you who are veterans know this already, that in the 5 or 10 minutes before totality, the thing to look at is not the sun, which has now become a little crescent, but the surrounding countryside around you that takes on this spectacularly eerie look. Shadows become very sharp-edged because the normal sun shadow, which is the same as a moon shadow because it's half a degree in size, and your shadow is dependent on the size of the object that's casting the light, plus the throw distance between you and your shadow, or the object and its shadow. So with the sun and the moon, your shadow, as you probably noticed, has a fuzzy edge around it, especially the parts of your shadow that are farthest from your body, like the shadow of your head looks particularly fuzzy. It has nothing to do with what you did the night before. Whereas the shadow of your knees and ankles are much sharper. That fuzzy area is the penumbra of your shadow. That's the partial eclipse. An ant walking through that sees your head partially eclipsing the sun. But a tiny point source of light doesn't have a penumbra, and that's what the sun becomes in that final, especially 5 minutes. The crescent of the sun has now shrunk down until it's only really a point, like a blobby star. And it's so small that your shadow and the shadow of everything is stark. And colors are also ramped way up and made more contrasty. And the whole scenery, it's as if everything is lit by, the world around you is lit by a different kind of star than the sun. It's like nothing else. It's so eerie and it's so worthwhile that it's not to be missed. Don't look at the sun during that time. Take the glasses off and just look around you. Then in the 1 minute before totality, you may see shadow bands. They're not visible in every eclipse. These are like wiggly lines, the kind of moving wiggly lines you see at the bottom of a pool. Except they're over the ground, they're everywhere. They're easier to see on a white surface, so if you're not looking at sand, spread a couple of sheets, and they will appear and shimmer. They make the hairs on the back of your ends and your neck stand on edge. Does everyone have hair in the back of their neck? Yes, okay, let's hope so. So that's, shadow bands are eerie, don't miss that. And as a shadow band, the shadow bands mean you only have a minute or so till the eclipse. And what I'm getting to is you don't want to miss the diamond ring. You don't want to be so conservative about not looking at the sun when the sun is still not totally eclipsed that you miss the diamond ring, which only lasts for a few seconds. You don't want to wait till it's dark. And if you've never been to an eclipse, it's never dark, so you don't wait for that. The darkest it ever gets at totality is about the brightness of a full moon night. Never gets completely dark. You can always read by the light of a total eclipsed sun. But you don't want to wait for that. So there's shadow bands. Things are getting darker. Things are getting darker. The bands are getting... Now, when the bands stop, totality, you certainly should look. But maybe you've missed the diamond ring effect by then. So how do you make sure you see it? You look too early, the sun is too big a blob, dangerous for your eyes. You wait too long, you've missed it. So this is an art, not a science. How do you catch it without missing it and still have eye safety? Well, this is what I do. Again, my lawyer, if I had one, would tell me not to tell you to do this, but this is what I've always done, and I've still have good vision after all these eclipses, the number of which I won't tell you, is this. Glance up at the sun when you see the shadow bands, or if there's no shadow bands, when it's starting to get darker. Take a quick glance at the sun. I mean a fraction of a second, just a quick glance. If it's a big blob there on the sun, just look away. And as long as you're not concentrating your vision on the sun, you'll be okay. Because the literature shows that nobody yet has developed a retinal lesion in under a few seconds. That's what it always says, a few seconds. Because a few seconds of staring at the sun concentrates the sun's not just visible light, but also UV on your retina and can actually do damage. And we're not talking about binoculars or telescope. That can do instant damage. And we're just saying looking at it. So you don't want to keep staring at it. But if you just take a quick glance and keep your eyes moving, you can check on it. So check on it, it's still a big blob. You look away, check on the shadow bands, look at how eerie everything is around you. You don't have to be very patient because this is only going to be a few seconds now before that goes from a blob to a proper diamond ring. Glance up a few seconds later, and now there's the diamond ring. It's only going to last a few seconds. Again, look at it, but don't stare at it. Look at it for a second, let's say, and then bring your eye to another part of the sun that's a ½ degree away. Let's say the opposite side of the sun from the diamond ring. And you'll still be looking at it enough to be able to see it clearly, but you won't be concentrating that heat or UV on the same spot of the retina. You'll look at the other spot, you'll look at another part of the sun. Just keep your eyes moving, and that's the safe way to see the diamond ring and not to skip it. Now, if you're more paranoid than that, and you say, oh, vision is too precious, I don't even want to take the one chance in a million, then don't do it. I'm not saying to do it, I'm just telling you what I do. Okay, so now there's the diamond ring, there's the beginning of the eclipse. What next? And what equipment to use? Again, we're back to you don't want to cut down the seconds of totality. So you don't want any equipment that you're going to be fussing with or that can mess up. Now, if you're so comfortable with your telescope that it's already set up and you can just watch it through the telescope, then of course do so. I like to spend about half the time observing just naked eye, just to catch the natural wonder the way humans and animals have seen it since time began. and then spend about half of the time with equipment. Even though I have a portable cast-grain and I've come to feel that the best equipment for me are image stabilized binoculars. I have 5 pairs of image stabilized binoculars. Marcy uses one. I use one at an eclipse. Press a button and it's rock steady, especially the 10 power ones like Canon's wonderful new 10x42 L is for luxury. They use their luxury optics. These aren't cheap. They're about $1,400 or $1,500, but you look through them, even at birds or anything during the day, and it's like there's no glass there. It's like real life, but 10 times larger and totally steady. And these newer Canons, you just press the button and a long press leaves it locked in stabilization. You don't have to keep the button pressed the way you did on the earlier models. And the sun's image is perfect. And with that magnification, you'll see the prominences and you'll see details. So things to look for that a lot of people neglect are, number one, you know to look for prominences. You know to look at the corona. But make sure you catch the shape of the corona. Now, the shape changes depending upon what part of the sunspot cycle you're on. Back in the 2017 eclipse, which I know some of you went to, we were near sunspot minimum. And so at that time, the equatorial regions of the sun have these big, broad coronal, they look like wings coming out of the middle of the sun on both sides. Near sunspot maximum, we're now in cycle 25, only a year or two from maximum, the corona extends pretty evenly around the whole sun. There's still nice irregularities. Those irregularities are great, but it's completely around. It's not confined to the equatorial end. So check that out. And in particular, my favorite thing is at the sun's poles, there are streamers, lines, black lines of plasma that follow the sun's north and south magnetic field as they head up and down from the sun. Make sure you look for that. There's really nice through binoculars. Binoculars will also see the smaller prominences that your eye might miss. Now, something that's mostly missed was brought to me by in that 2017 eclipse. When Marcy was still using her binoculars, she's been a school teacher for 37 years, kindergarten teacher, smart lady, using the binoculars, and some of the rest of us were looking at the sun, and we realized the totality was about ending. We knew the diamond ring was any second. It was brightening up on the edge, and we had long since put our binoculars down. Oh, that's for safety. Use the binoculars for maybe a minute or a minute and a half in the middle of the eclipse. That way, there's no chance that you'll still be using them when the sun comes back. So what I do is look at the sun just by itself for the first half minute or minute. Then I use the binoculars for a good fat minute and a half, and I put them down and again look naked eye for the final part of the eclipse. That's the safest. Anyway, that's what we did. And all of a sudden we heard Marcy shouting out, "Oh my goodness." I think she said, "Oh my God," actually. The whole right side of the sun has turned purpley red. What was she seeing, folks? The chromosphere. I knew somebody here would call that out. Absolutely right. The freaking sphere. I'd never seen the chromosphere. You know, all those nice pink, red prominences are pieces of the chromosphere jutting out into the corona. But the chromosphere itself is this red, it can vary from pink to like purpley red, sphere that covers the photosphere of the sun. It's the next layer up. So you're going to see that first when the eclipse is over. It's going to expose itself, but only for maybe 3 seconds, and then the blindingly bright photosphere will come back. Photosphere is an amazing thing. That's the visible layer that puts out the light. You know that it's only a couple hundred miles thick? The sun is 865,000 miles across, and the part that gives off the light is 200 miles across. It's like painted on. It's like a shellac covering. Anyway, before that brilliant part comes out, there is that red photosphere, and it's also not a broad layer. It's about 2,000 miles thick, but still, it comes out first, but only for a few seconds, and then the blinding photosphere. So you have 3 seconds to see it. She had seen it because she didn't know what the hell she was doing. And she put down the binoculars probably with 1 second to spare and saved her eyes with a second to spare. Now, who would be dumb enough to try that? Well, you know, of course, Bob on the next eclipse in Chile in 2019. I didn't tell the people about the photosphere there. I thought, oh, that's just too perilous. But on the next one, I said to myself, I got to try that. So kept the binoculars on after totality was over, and there it was, and I immediately yanked it down after a second or so. The chromosphere, the chromosphere. Ah. So anyway, that's something, it's up to you to go for that. I'm not saying you do, but you know, there it is. At some eclipse, you might want to try for it, and at some eclipse, we've learned so much about eclipses. You know, I'm going to show you the spectroscope that I hope you've read. I mean, back in the old days, Valerie and I were looking at this old textbook from 100 years ago about the sun. Back then, what did they know? What did they know about the sun? Well, the reason the sun is hot. You know. That'd be religious revival, maybe. Okay, so some of you know what this is. It's a nice spectroscope. You don't want to get one of the little floppy cheap ones. You want to get like only about $150. And it's so much fun. You go around, you look at street lights, you see the mercury in these fluorescent lights. There's mercury and argon, and then you see the emission lines of this and in everything. You look at clouds to see the solar spectrum. You see the whole Fraunhofer lines or dark line spectrum of the sun. It's so much fun. I have a spectroscope for my observatories, and one of the nice things to do with the spectroscope with stars is that, as you know, through a telescope, everything is pastel. There's no deep saturated colors. Even the stars that they say are red, you know, like they say Antares and Betelgeuse are red supergiants. They're not red, they're yellow-orange. If you really honestly compare a swatch from a paint store to what you're seeing through the telescope, yellow-orange, not even as deeply colored as a pumpkin. And you wouldn't call a pumpkin red, but books say red supergiant. It's a description of that type of star. It's not supposed to be actually a color description. You know what Marcy's doing right now? She's going like this, indicating, Bob, you're going over your 15 minutes. Okay, so thank you, Marcy. That's what she's supposed to do. So because we're looking at pastels, you know, the red stars are only wimpy pastel. Every color is mixed with a lot of white, because every star also puts out green, red, and blue, which combined are seen as white by the human eye and brain. And that white light mixes with the excess color and makes it a pastel. Every star looks pastel. So when we have visitors to the observatory, school groups, scout groups, whoever, friends, you'd really wow them if you showed them something that was deeply, beautifully, brightly colored, as bright as a rainbow. And so that's where a spectroscope comes in. Hook that up. Look at a star like Vega of spectral class A. Spectral class A are the best because their colors are very rich, and the H Balmer series of hydrogen is very clear. H alpha and beta and gamma delta. Nice black lines, blacker lines than you'll see in other spectral classes. But it's the colors that I'm talking about, richer than a rainbow. So you have a spectroscope, you tell them a little bit about it and say, this is how we know what a star is made of. So you give them a little science, but what they're really getting are those colors that they've not seen in anything else you've shown them, like a blast of deep color. Where was I going with this? Marcy's going like this, and then she's tapping her wrist again. Okay, so it means time to quit. Thanks, everybody. Thank you.
So what you guys don't see behind the scenes when we do the radio show is that the host, Ray Graff, also does similar hand motions when we're both talking, right? It's not just Bob. Sometimes I'm a bit long-winded too. Are you putting up my presentation? You're the best. You're the best. Well, first of all, I wanted to thank you guys so much for the invite back. It was so wonderful to see everybody again. And I'm just reminded how amazing this club really is. And the people that are here are just phenomenal. You don't tell everybody else, but you're definitely the best astronomy club in New York State. And I've seen a lot of them. So you guys are definitely the best. Yeah, no, take your time. So I just had some pictures and things that I want to show you that Mark is going to help me pull up. But Bob wanted to talk about observing. You know, with the eclipse coming up, there are a lot of things that you all can visually observe, whether it's with your eyes alone or through a telescope or equipment. And I wanted to inspire you guys to do a little bit of citizen science. I want you to take pictures, not necessarily of the eclipse. I'm not going to talk about the eclipse at all today. But I did want to talk about some citizen science projects that you might be inspired to do. And I want to show you what we are doing at Oneonta to help inspire you and show you that everybody can do it. You know, the moral of the story is if I can do it and my students can do it, any one of you with a telescope and any of the equipment up at the Farish Center, you can do it too. Are you going to click for me too? Oh, you're the best. Okay. I don't usually have this in a lecture hall. I got to do it all myself. So I just want to show you briefly what our equipment looks like so that you can see that it's very similar to what you all have here. So we call ours the College Camp Observatory. It's about 3 miles north of SUNY Oneonta. And it has very similar skies. We're technically a Bortle Class 4, and I looked it up, and this place is about a Bortle Class 4 too. You can see all of our domes there. The big domes have large telescopes in them. The smaller domes are empty at the moment. And the garage in the back, thank you. The garage in the back has something special in it that I'll show you in a minute. If you could go to the next one, please. Excellent. So our tallest dome there has a 14-inch SCT. It's a Celestron. It is the smallest of our telescopes that are set up, but it is the most modern. It actually hooks up to my laptop like most modern telescopes today do. Everything else we have is a bit older, and it's been a real challenge over the last couple of years to get it all situated. So this is the one that we're using for most of the work that you're going to see. You can go to the next one. This is an old 16-inch Meade, which currently has a broken focuser, so we haven't used it too much. But aside from the 14-inch, that is the one that we will use a lot. And then the next telescope I'm going to put up, and my dinner table is not allowed to answer the question because we talked about this. So this is a 40-inch diameter telescope. It is the largest telescope that a college owns in New York State. And do you notice something less than ideal about this telescope? Yes, it's on wheels. It's on a trailer, and it lives in that garage, and that is not a roll-top roof garage, to my dismay. You literally have to call the groundskeeper to get him to pull out his truck, to hook the trailer, to pull the telescope out onto the gravel, and set it up and use it. So this is going to be, in the very near future, the main telescope that we use for research. In the future, we still have to raise money for the building, but we do have some funding to upgrade it. I can talk later about what the issues are, but basically this telescope, the technology is early 2000s, and it doesn't plug into my laptop. It's a whole ordeal. But you can look through it. We do visual observing. The planets and the moon look spectacular, and it's going to be really great for citizen science going forward. Next, please. And we do have a lot of cameras too. A lot of S-Big cameras and things were purchased in the past, spectrographs. So we have a lot of CCDs available as well. Next. So the main citizen science project that I'm working on, that I hope that many of you will ultimately do after this short talk, is talking about or looking at exoplanets, and we observe exoplanet transits. I'm sure most of you are familiar with the concept of an exoplanet transit. This is supposed to be a little video. It's fine. It doesn't have to play. But you can see the star here. The little black dot is the exoplanet. And as the planet orbits around the star, it will block some of the starlight as it moves in front. And if you track the brightness of the star over a few hours or throughout a whole night, you can make the graph on the bottom, which is a light curve, the brightness versus time. When the planet moves in front, the star dims. When the planet is not in front of the star, it moves, the brightness goes back to normal. So we can take pictures during planetary transits, and we can make our own light curves. If you could put that up. So the picture on the right is a light curve that my students made using the 14-inch telescope. And what you are looking at here is essentially time. The zero in phase here is the center of the transit, so it's just been normalized to that. And then this on the left is relative brightness of the star, where 1 is the average 100%. And our data points are the gray dots. The red is a nice fit, and the blue is some averages there. But you can see that we clearly see the star dimming. This is a couple hours time, and then going back to normal brightness. And this is an exoplanet system called Kelt 23AB. It's a Jupiter-sized planet that orbits a sun-like star in about 2.2 days. So every 2.2 days, it whips around and produces this. So my students were able to do this in about 5 weeks of training. They learned how to use the telescope, they took the data, they analyzed it, and they made this graph. And I hope you're not thinking, well, I don't have a PhD, I'm not your student, I can't do this. Yes, you can. That's what I want to convince you all, is that nowadays there are so many websites, tutorials, free software that you can use that will teach you how to do this. So if you could go to the next slide for me, Mark. Yeah, this is fine. It's fine. It's going to fill down, so you're going to have to keep moving it. Sorry. But I can come back, and I will happily do this if you want, maybe a virtual talk in the future, to give you all the details about what I'm about to say, because this slide could be an hour-long talk. But I just want to point out that you can do this from start to finish. Your first question should be, well, how do I know where to look? When do I know when a planet is going to transit the star? There's a website for that. Here's the website. I can give it to you later if you could click for the picture. I'm going to just show you, what it looks like, and I'll give you the example for Kelt here. But basically, you get information about the star. All you have to do, by the way, is type in your location, the night you want to observe, and the website gives you an entire list of exoplanet transits, exactly when to look and where. You've got the magnitude, the time that you should look. If you enter additional parameters, it'll even tell you exactly how much of the light curve you expect to see, and then how frequently it will orbit and the position to point your telescope. It's all there. And all you have to do is say, I'm in Ionia, New York. I have this telescope. I want a limiting magnitude to be 12 or whatever you want. And it's all right there. You'll get 100 different options to look at. Next, please. Then you got to take pictures. I'm assuming that you all, can take your own pictures. And there is software for you to use. I like AstroImageJ that is very user-friendly. You can clean all your images, you can do photometry, and you can get all of those data points. Next one. And then that red line, I didn't draw that red line. The software called Exotic drew the red line for me. I fed it the data, and it gave me a nice fit. And what we can learn from the fits of our data is the size of the planet. Depending on how far down the light curve goes, that tells you how big the planet is compared to the star. And all of that is done for you with this, again, easy to use software. So if you go back just for 1 second, sorry. The team that I joined that kind of put this last piece together, Exotic, it's called Exoplanet Watch. It just went live to amateur astronomers. For a couple of years in the trial period, it was just for professional astronomers to work out the kinks. But I joined it a few years ago, and it's a team of astronomers of all levels across the world that teach people how to do this. You can go to weekly virtual meetings, and you can learn how to process the data, and then you can submit your work, and they publish it. It's really, really amazing. Now you can go to the next one. So why would you want to do this, right? I mean, I'm an exoplanet junkie. I like them. I think it's fun to watch this happen live, but there's a million reasons that you should do it for scientific purposes. If you're not familiar with TESS, the Transiting Exoplanet Survey Satellite, it's a telescope that replaced the Kepler Observatory. There's 6,687 candidates as of last night when I checked, where the team needs observations of ground-based telescopes to check and make sure that what TESS identified as an exoplanet actually is a planet. And they can't do it with the space telescope. They need all of you to take these pictures to make those light curves and see if the planets are actually there or if it's a false positive. Next. I don't remember what's next on the list. Perfect. Right. So even if we find exoplanets, you've got on that website the whole list of known ones, a lot of those were discovered 10 or 20 years ago, and nobody's really looked at them since. We need to refine the transit timing, how fast they transit, and when we actually would expect them to transit in 2023 and in future dates, because professional astronomers are going to want to use telescopes like James Webb to look at these. And if the timing isn't quite right, they're going to observe essentially nothing. They're going to miss the transit. So by refining the timing from observations that you all can take, you can help professional astronomers get the data that they need. You can also discover new planets. If you watch the same planet over many, many orbits, you can find what are called transit timing variations when the planet doesn't orbit quite at exactly the time you would expect, which could be because of gravitational tugs from other planets in the system. So there's the possibility of discovering a new planet. And then the last one, of course, is that you can get published, right? I mentioned that you can submit your data to Exoplanet Watch. I'm pretty sure that's what the last bullet point is there. That's fine. But your data with a small telescope or the telescopes here at the Ferris Center, that can get published. You can become a co-author on a paper, and you just have to take the data. They're not expecting you to have a PhD and contribute to the theory or anything like that. They just need the data. There's not enough telescopes and not enough people out there that are doing this work. So if exoplanets are not your thing, I just wanted to brag a little bit about what my students did this summer, because with all of the smoke and the cloudy skies, exoplanets wasn't something that we were able to do. But thanks to Dave Bishop alerting everybody about the supernova and M101 and keeping his website up to date so that we could track it, we were able to take a look at M101, spot the supernova, and we got 4, 5, 6, 7, 8 nights. This was like that weird, I don't know if you guys had it too, but in Oneonta, we had like a week in May around Memorial Day where it was like crystal clear every night. It was right after finals and I was there every night. And then these other data points were just later on. But what you're seeing here is the light curve for the supernova. Again, we're tracking time versus magnitude. The Oneonta data points are the 8 black ones, and the red ones are from the AAVSO, the American Association of Variable Star Observers. So you can see that our data points follow the trend. We expect supernova to dim over time. And all of this work, again, is looked at by professional astronomers. They use this to figure out what type of supernova they're looking at, what the progenitor was, and all of that. So if you don't like exoplanets, you can do this kind of work with supernovas if exploding stars are your thing, and contribute data to citizen science projects that way. So I just wanted to wrap up again by saying that, if we can do it, if I can do it, you can do it too. And I would love to collaborate with the professional and amateur astronomers amongst all of you and do some of these projects. And in a couple of months, our big 40-inch telescope will be online, hopefully, fingers crossed things go smoothly, and we'll be able to do a lot deeper observing and a lot more observing than we're able to do now. But citizen science is for everybody. So I hope you will observe the eclipse and do all of the wonderful visual observing, and also consider learning how to use the equipment to take pictures and do citizen science too. So I'll wrap things up there, and I think we'll do questions.
Valerie,
Yeah.
what exactly, I'm not just an observational astronomer. What exactly piece of equipment do you use to measure the actual amount of light that's coming from the star that you're observing, the exoplanet transit?
Right, so we have an S-Big CCD camera that we're using to take pictures. We don't do it with a DSLR, although exoplanets is one of the things you can easily do with a DSLR. Because the filter doesn't matter so much, and the colors, it's a little bit better if you don't, but it can be fixed. So if you're just measuring the total amount of light, you're comparing the star you care about to a star that you don't care about that's consistent, and all you care about is the change. So we use CCDs, but a DSLR or something similar would work as well.
Software would then interpret how much.
The software that we use is called AstroImageJ, and yes, it basically does that. All you have to do is pick a circle size, draw a circle around the stars, and then it will automatically do the measurements and the statistics for you. So you don't have to do any math yourself, which is the lovely part. Yeah.
Using a V filter as well, or just Ross.
So we do ours through the V filter. If you do test targets, TESS has a naturally red filter built in because it looks at smaller stars. So I would suggest that. Depending on what system you pick, you might want to have a filter wheel, but it's not 100% necessary. So far, V-band has worked well for us, but R-band might be the way to go. Yep.
What kind of exposure times do you want to do for that? And is it just something where you just do continuous exposures for a period of several hours?
Yeah, these are great questions. So the exposure time is going to depend on the magnitude of the star. The Kelt star happened to be about magnitude 12, so it was relatively bright compared to some of the other targets. So we were doing approximately 15 seconds. That's it. We did a 15-second image every minute or two, and then we did that for about 3 hours because you don't want too much time in between your data points, especially as the planet enters and exits the star. But yeah, you just set it up. If you can keep your telescope aligned at that target, you can just tell it to keep continually taking pictures of the same exposure time, and you're good to go. And if people have questions for Bob too, I can stand down. Yeah.
Now, what do you think is a good minimum length?
Well, so there's trade-offs, right? We're using the 14-inch because it's the one that works. But you don't have to use a 14-inch telescope. There are a lot of people on the Exoplanet Watch team that are using 6 or 8-inch apertures, so you can go relatively small. And smaller telescopes will generally give you a larger field of view. So you can align on a target that you know is transiting, but you could check all the other stars. If you've got 30 other stars that show up in your frame, you could check all of those for unknown exoplanets as well. So I've seen them be, really small from this team, but they could go large as well.
To follow up on that, Valerie, how big was the telescope used to discover the first exoplanet you ever discovered?
Oh, I don't remember off the top of my head. That was the weird one around the white dwarf, though. Is that what you're talking about? That's technically the first one. Oh, 51 peg. Is that what you're talking about? I don't remember. Do you remember? Beating me? 5 inches.
First transit was 5-inch telescope.
That makes sense. There's other telescopes like have you ever heard of Super WASP? Super WASP is not a telescope. It's a set of 8 Canon camera lenses that is on essentially a telescope mount, and that's what they're using to find exoplanets. I don't know how big the lenses are, but they're something like this. They're not that big. Cool. Other questions? Anybody want to talk to Bob? Or if Bob's eating, I'm happy to keep answering, but
Well, are we doing dessert or are we doing the panel?
we're kind of just doing both. We're just flow. We're winging it.
Some people have dessert. It's not fair for the others to look on and see. Dessert's more important than anything we have to say.
Tony, go with your question, then we'll let.
You mentioned that you hadn't been to a group like ours on the path of a total solar eclipse over the next year. Have you ever been to like a educational institution that was on the path? And did anyone ever try that you have some fancy piece of equipment that everyone wants to look at the sun or the eclipse with, let's say, the best solar scope on the site, and how did you allocate that time? Or are you familiar with how they might have allocated?
Okay, when it comes to allocating telescopes, now what I do is give talks at like the Texas Star Party or the Peach State, the Georgia or outside Chicago, and I don't allocate telescope time. I mean, usually after my talk, I love drifting around the scopes, and some people have even scopes almost or as large as yours there. And just listening in and seeing what people are into and what they're observing, because I use it in my articles. That's what I do, but I don't ever allocate telescope time. And so far as totality coming up, remember, every given spot on Earth only gets totality once every 360 years on average. And if it's cloudy, you wait another 360 years. So the odds of me giving a talk and then in the next year there's going to be an eclipse is very small. It's the case here. It's amazing, and I'm really both a little envious and really glad for you, and a little nervous for obvious reasons. I must say that this time I have to take our group of about 40 people to Texas to a winery / ranch that's been rented out for this eclipse. And at that time that it was set up about 2 years ago, I thought, well, Mexico's the clearest place on the eclipse path, but we'll all be kidnapped if we go down there. So we're not going to do that. So the next best would be Texas, and that's going to be clear. And here in the Northeast, it's a crapshoot, it's 50-50 crapshoot in, early April. But now I really see the data is showing that it's only a 10% greater chance of clear skies down there than here. And if I could, I'd rather, this is the Northeast of my country here. So I'd rather be here, and just for the sake of being here in this area, if I could. Yeah. Yes.
So in theory, one could try to use cell phones or some similar timing device with a group of people at an eclipse to say, it is now 10 seconds before totality, do X, Y, and Z. Okay, totality, X, Y, Z.
Yes.
Have you ever considered doing that? And are there reasons not to try it?
No, it sounds like a good idea. There have been eclipses that have been on, one in the Black Sea in 1999, I think it was, on August 11th, the same day as the meteor shower, that they, Ted Pettis was running that one, and I was the eclipse astronomer on the ship. So I announced to everybody that I always do, that I'll talk to them privately, I'll talk to them publicly, right up to eclipse day. But at eclipse time, I am not going to open my mouth and ruin this eclipse with talking, with narration. You know what to see. It's a sacred event, as I said. You don't want to hear somebody jabbering about, oh, and there's this and there's that. No, the time for that, it's over. So they gave us the crow's nest. Marcy was there, and we had our 2 kids who were little at the time, and we climbed up to the crow's nest of a ship. Can you believe that? Fortunately, this little 3 or 4 foot area did have a metal little high railing around it, so it wasn't quite as scary as that. And they ran up. I don't know how they got a 1/4 mile microphone cord up to the crow's nest so that I could theoretically talk about it. But I only did so going into the partial phase, and then I told everyone, that's it. I'm going to speak no more. But then another ship pulled from a distance, came closer and closer to ours. They must have seen ours at anchor, and that other ship's captain must have thought, well, that must be the place. So they came close enough to us that we can hear their PA system, and some idiot was jabbering during the entire totality. Fortunately, we couldn't make out his words, but we could make out that the jabbering was going around on the PA. So to answer a question that I don't think you asked, no, I don't talk about this stuff ever on eclipse day. An app to count it down, that sounds good. But that's still, at what point, that would tell people when it's safe to look up. Yeah, that's a good idea. Yeah, assign one person to be the person who gets blind, and then you'll miss the diamond ring. Yes, if they say put your glasses back on at the end, you're going to miss that last diamond ring. Oh, here's that thing about that last diamond ring. When that diamond ring comes at the end, it starts out, of course, it's a reverse order. So it starts out as the beautiful diamond ring you do want to focus on. But then it grows bigger and brighter and bigger and brighter. And there's a psychological factor, speaking for myself, you don't want totality to be over. And proof that you don't want totality to be over is that partial eclipse, that hour-long partial eclipse that everybody enjoyed looking at with their filters, after totality, nobody bothers with that second partial eclipse that lasts an hour. Everyone gets in their car and goes home or goes out on the tour bus or whatever. Nobody bothers. So it just shows you totality is everything. So when that second diamond ring comes in, it means it's over. You don't want it to be over. So you keep looking at it, getting brighter and brighter, brighter, but you're staring at it. It's a diamond ring. It's still part of totality. You keep looking at it and looking at it. That's the thing to guard against. Just look at it those first few seconds when it's the diamond ring. Then as it starts getting bigger and brighter, really don't do it. It's like, saying kids don't use drugs, Yeah, you use welder's glasses with a helmet, and then, in fact, we do. We have welder's goggles, so you don't have to hold them with your hand. They're not expensive. That's the best way to do it, I think. Question back there? Yeah. Get the kind that come in a nice wooden box, and those are really, really good for eclipses. And one of the things to look for is the flash spectrum. Those of you who took astronomy in college know that helium was discovered, I think, in 1868 or something. At the end of the 1800s, helium was discovered first on the sun, not on the earth. That's why it's named helium, after the Greek god of the sun. And you'll see it, you hear about the flash spectrum. The only time that the sun spectrum turns from Fraunhofer lines, dark lines, absorption lines, in other words, to emission lines. And you actually see some emission lines from the sun when during totality. So through a spectroscope, if you want to do it, that's just for a few seconds, but it's a bit of a thrill. That's all I was going to say. I'm sorry? The vendor, I forgot. There's a few different models. The one that I like best, I bought a few. One of them has a single straight tube, but this other one is nice because it has a comparison spectrum, and it also reads out the wavelength in nanometers. Actually, it's in angstroms, which we prefer. We used to have fights over this. The people who were just into plain physics were into nanometers. They still do it. And only astronomers and astrophysicists speak in angstroms. It's like old-fashioned talk, but it's sort of like an in language. So anyway, this is graded in angstroms, which we love. So just look online, and they're only about $150, the best ones. That is, they use prisms instead of gratings, diffraction gratings. And this one is a 5-spectrum prism, comes in a nice wooden box. They're not expensive. Any other questions for Brown or anyone?
I had a question about the 40-inch telescope. You're using that bird, obviously, to make it more stationary, but what other upgrades are you going to do to that?
Yeah, so right now the 40-inch telescope has a hand paddle from like the 1990s. And the hand paddle actually only functions on equatorial mounts, the ones that are polar aligned pointing towards the North Star. And those of you that know telescopes saw that that was an ELT-as style mount. So right now we can't take a hand paddle or a computer and type in what we want to look at and have the telescope move there. We have to manually push it. Which is fine for the easy to find objects. And I was telling my dinner table this earlier, you'd think it'd be easy to use the finder scope as well, but you have to get on top of the trailer to look through the finder scope, and then the tires flatten, so the whole telescope goes, and then the finder scope is like 5 inches because you've got it on the back of a 40-inch telescope. So it's got a relatively small field of view. So any of you star hoppers out there, it doesn't work the same. So the setup is just not ideal. If we had modern software that we could just type in and say, point to the Andromeda galaxy, and it would get us 99% of the way there, that would be ideal. And that's really what we're going to focus on. And then in the future, we're going to mount that thing on the ground so I never see wheels again, and we'll be able to really use it for research. But that's the main problem right now.
Any other question? I realize that by going on like this, we're depriving you of dessert. I've never had an audience that had maybe, hopefully, split feelings. Do we want to hear more of them? Or
Cake or Valerie and Bob, right?
Because the moment you get us to shut up,
I'll do you next.
You may have mentioned this, but where did that 40-inch telescope come from originally?
So it was purchased by the college. It's a JMI telescope. I think they're out of Ohio. Yes. Jim's Mobile Inc. is what JMI stands for. So yeah, it was purchased in around 2006. And the reason it's on wheels is because it was purchased with a grant that was intended for outreach money. And the original idea was that we would wheel that to schools and let little kids look through it. And I'm like, why? Why would we do that with a 40-inch telescope? The eyepiece straight up is 7 feet off the ground. What third grader is going to climb a ladder to look through it? So it's just that I don't know. I mean, I'm not disappointed to have a 40-inch telescope. Please don't take that away. It just was not conceptually designed well in the beginning.
I just, you've been to so many eclipses. Was there anything from like a public safety or logistics or municipal standpoint that ever stood out to you? Like they did this really well, they were really well prepared, because we're bringing a lot of traffic to the area too, and there's committees for that. I just was wondering if anything stood out.
Yeah, the question is about public safety and the logistics of eclipses. Some eclipses have traffic jams, like the kind that you'd have after a fireworks show, where you're just in traffic. We had it in 2017 up in Wyoming. If you tried to get back to Boulder or Denver after that, it was like you definitely missed dinner. It was like a 6-hour traffic jam. I was glad to see it, because when do you have in America traffic jams because of a natural event like an eclipse? I was glad to see there was so much public interest in it, but that can happen. Fortunately, many paths are so long and there are so many choices of places to be that you pretty much avoid traffic jams. So far as where you're going to set up, municipalities are so about, in some places in that 2017 eclipse, stadiums were set up, schools set up sports stadiums for it. In other places, there were supposedly hotel parking lots that were roped off, but from personal experience, sometimes that doesn't work. It's best to get to a private spot if you can. And you don't need much, you just need to see the sun. So you don't really need what's around you isn't very important.
Should we let them have dessert?
Yeah.
This is like a Marie Antoinette kind of thing. Yeah. All right, thank you, everybody.
Yeah, thank you.